Hello everyone, my name is Arpit Singh and in today's video we are going to solve the second internal test for numerical analysis and design. We are going to see solution of every questions in second internal test. The first question is write algorithm for Newton's forward difference interpolation formula. As we can see that Newton's forward difference interpolation formula is like if we have to find value of fx, we have to find value at x naught plus u, the where u is defined as x minus x naught by h, u into forward difference of x naught plus u into u minus 1 by 2 factorial, the square of forward difference of x naught and so on, where n of y0 is equals to nth forward difference at the first row. Here the y naught forward difference of y naught is like the first row forward difference from the first row. We can put this formula in algorithm like like we take value of n x values from 0 to n minus 1 and the value of corresponding fx to 0 from 0 to n minus 1 as y. While constructing the forward difference table, we loop from I to we loop from 1 to n minus 1 and another inner loop from 0 to n minus 1 minus I. From this loop, we create a difference table as shown, and now we get value of x for the interpolation from the user and calculate h by x1 minus x0 and calculate u by x minus x0 by h. We can initialize result by y0 and while computed interpolated value, we for I from 1 to n minus 1, we compute u turn, which is u into u minus 1 into u minus 2 and so on. And result, we append the result plus is equals to u term into difference table. This difference table 0 and I position divided by I factorial. And we output the our interpolated result at the end, which is this result. In second question, we have to write Python or C or R code for Newton divided difference interpolation formula. The Python code for Newton's divided difference formula is like we have two functions, def divided difference for creating the divided difference table and def Newton divided difference for calculating the value. The divided difference function take three parameters x, y and n. It first created the empty divided difference table 0 for underscore in range. In n it created n cross n with every values filled inside it as 0. Further, for I in range n, it stores yi in divided difference table and then subtracts it using to loop and again stores it in divided difference table. This function returns divided difference table after creating it fully. In Newton divided difference formula, we initialize n with len of x. X is how many terms are there in the argument. We create a variable table in which divided difference x, y, n pass the values. Result for now is generalized as table 0 cross 0 position of the table, and we initialize a product term with 1. Now for using for loop, looping from 1 to n, we calculate product term and we further multiply product term with the divided difference table 0 cross ith value and sum it to the result. Then the value, interpolated value gets calculated in the result, so we return result at the end. Example usage, we have x 5, 6, 9, 11 and y 12, 13, 14, 26. We have to find interpolated value at 7. So interpolated value will be found if we pass x values, y values and x p, in which value we have to interpolate to the function. So this function returns the interpolated value to this variable. Third question, we have to prove that sum of Lagrange coefficients is 1. To prove that, we have Lagrange interpolation polynomial is defined as Px, in which I summation Lix into Fxi. where each Lagrange basis polynomial is x minus xj upon xi minus xj, pi from j to 0 to n. We have to prove summation of Li x from I to 0 to n is 1 for any value of x. Assuming we construct a Lagrange interpolation for the constant function, fx is always equals to 1 for all x. Then the interpolation polynomial is, if we replace fxi to 1, then we get n from I to 0 to n lxi by px. But since this function is constant, the interpolation must return the same constant value at any x. So this proves px is also equals to 1. Hence, we prove that the sum of Lagrange coefficients is 1. Fourth question is, obtain Simpson's 3 by 8 rule from general quadrature formula. We note that general Newton-Cotes quadrature formula over integral a b is defined as integration from a to b fx dx is approximately equal to summation from 0 to n wi into fxi, where x0, x1, x2 are equidistant point and wi are weights associated with them. For Simpson's 3 by 8 rule, n is equals to 3, that are 4 point. The 4 points are x0 is equals to a, x1 is equals to a plus h, x2 is equals to a plus 2h, x3 is equals to a plus 3h. We map x from x0 to x3 to standard interval using x is equals to x0 plus ht, where t maps from 0 to 3. We can define t as, if t is equals to 0, x is equals to x0. If t is equals to 1, x is equals to f1. If t is equals to 2, x is equals to x2, and so on. We now rewrite the function fx as fx0 plus ht and integrate h into integration from 0 to 3 fx0 plus ht dt. We integrate this function with respect to t. If we integrating, we get 3 by 8. If we integrate this function, we will get 3 by 8 f0 plus 3f1 plus 3f2 plus f3. If we replace the corresponding values of this f functions, we get 3h by 8 fx0 plus 3fx1 plus 3fx2 plus fx3. This is the Simpson's 3 by 8 rule. We have to derive it. Obtain Simpson's rule from Newton-Cotes formula. In this question, we have to derive Simpson's 1 by 3 rule using Newton's closed formula with n is equals to 2. The closed Newton-Cotes formula approximates like same as the above question from a to b fx dx is approximately equals to summation 0 to n wi fxi. Here there are n plus 1 points are equally spaced with step size h is equals to b minus a by 2. So the 3 points are x0 is equals to a, x1 is equals to a plus h, x2 is equals to a plus 2h is equals to b. Here we also map x is equals to a plus ht, where t maps from 0 to 2. Integrating this function, we get integration 0 to 2 ft dt is approximately equal to 1 by 3 f0 plus 4 f1 plus f2. Therefore, integration a to b fx dx is equals to h by 3 fa plus 4 fa by a plus b by 2 plus fb. This is Simpson's 1 by 3 rule. Question number 6. Solve dy by dx is equals to 1 by x square. Y0 is, we have to solve this. Dy by dx is equals to 1 plus x square. We have given that y0 is equals to 1. We have to find y1 in steps of 0.5 with Euler's modified method. Euler modified method is defined as, first we have given dy by dx is equals to 1 plus x square and y of 0 is equals to 1. So we have to find y1 with step size 0.5. Yn plus 1 is defined as yn plus h by 2 fxn yn plus fxn plus 1 y star n, where y star n is defined as yn plus h into fxn yn, and fxy is defined as 1 plus x square. It's just a way of writing it. So fx0 plus y0 is equals to 1 plus 0 ka square is equals to 1, and y star 1 is equals to y0 plus h into fx0 y0. So fx0 y0 is equals to 1. So this equals to 1.5, and fx1 into y star 1 is equals to 1.25. So y1 is equals to 1 plus 0.5 by 2 into 1 plus 1.25, which is 1.28125. Now x1 is 0.5 and y1 is equals to 1.228125. So we again follow the same procedure as above and calculate f x2 and y star 2 is equals to 2. So from this value we can calculate y2 is equals to 2.09375, which is the value of y at 1. We have to find y1. So this is the value of y1. Find the value of pi from integration 0 to 1 dx by 1 plus x square using 3 points Gaussian quadrature formula. Gaussian quadrature formula is for interval -1 to 1. So we transform the integral to standard form like integration -1 to 1 f 1 plus x by 2 into 1 by 2 dx. So now we can write the function as integration -1 by 1 plus 1 plus t square by 2 1 by 1 plus 1 plus t square by 2 into 1 by 2 dt, where this can be written as integration -1 to 1 gt dt, where gt is this function. For 3-point Gaussian quadrature and weight, there are 3 point minus root 3 by 5, 0, root 3 by 5, where weight is associated with them are 5 by 9, 8 by 9, and 5 by 9 again. Now we evaluate GTH for t is equals to -0.7746, x is equals to, we replace t, so x at t is equals to -0.7746 is 0.4379. For t is equals to 0, x is equals to 0.4. For t is equals to 0.7746, x is equals to 0.2796. By applying Gaussian quadrature formula, we calculate that this integration is approximately equal to summation 1 to 3 wi fxi. If we calculate this and sum all this coefficient with respected values, we get approximately value of 0.7852, which is the value required.